recording. One moment. Okay, sorry. I have told you something about the free carriers as a function of the temperature. In the freeze-out zone, not all dopants have um, accepted or donated. In the extrinsic zone, all donators are assumed to have generated a mobile electron. And in the intrinsic zone, we have said that the intrinsic carrier concentration exceeds the doping concentration you have generated. So, this is the common sense now for the next slides. From now on, we are always in the extrinsic area. Okay. So the assumption, the doping concentration, donator or acceptors are much larger than the intrinsic one. And all impurities are activated. This is the assumption. I summarize some verbal expressions now by equations. For the intrinsic carrier concentration, the Fermi level is equal to the intrinsic level. It's the center between the conduction band and the valence band. Usually, it's roughly really the center, but we have some deviation, which is a function of the imbalance of the effective density of states. But for our lectures, it's okay if we take this into account. Okay, point one. Point two, if we have an N-type semiconductor, we can calculate the distance of the Fermi level to the conduction band edge by comparing the density of the effective density of states in relation to the doping concentration. And if we refer the Fermi level to the intrinsic level, then we compare the doping concentration to the intrinsic carrier concentration. Okay, so these are the same topics like we have had here and here. So if you know this value is ND and this value is NA. So if you compare NA to NV, then take the natural logarithm, and then you have this difference. And so if you solve for this part, you get either this equation or this equation. Just the same equations, but solved for the distance of the Fermi level, either to the conduction band edge or to the intrinsic level. Okay, and this for the N-type and P-type. Therefore, we have four equations. The most interesting way of calculation is here marked in this area. So let's calculate for a given doping concentration this distance to the intrinsic level. Okay? Let's take an example. So ND should be 10 to the power of 16 per cubic centimeter. Okay. Then the intrinsic carrier concentration should be 1.5 times 10 to the power of 10 per cubic centimeter. Okay. Now, what is, so we have a donator, so we have an N-type semiconductor. Therefore, uh, as we have given the intrinsic carrier concentration, we calculate the difference between the center and Fermi level. Okay, so the Fermi level in the N-type semiconductor minus the intrinsic energy level is equal to the Boltzmann constant times T, the temperature, times the natural logarithm of 10 to the power of 16 divided by 10 to the power of 10. Okay, this is equal to, the temperature should be 300 Kelvin. And I would like to you to find out the Boltzmann constant with the units of the Boltzmann constant in electron volt. Can you give me this value? Yep. I should have this value here. 1 second. So you could see also the colorful ball, right? Now it's over. Here we have it with the unit joule, and here, yeah, you're right. So the value is 8.562 to the power of 10 to the power of minus 5 electron per Kelvin. So I switch back. Whoa. 0.357 electron volt. Okay, can somebody confirm this result? I just take my very fancy pocket calculator and uh, start the very fancy pocket calculator. You know this pocket calculator? It's HP. It's an HP pocket calculator. The physical one is out of order. I have used this during my study time. Now I have this. Exactly. So somebody has programmed, written a software, an app, which imitates his lovely pocket calculator. Okay, so 8.62 to the power of, no, not space, the power of 5 minus, uh, 8, return. And then 6, and then where is the logarithm? Long time not used. I skip it. A second, a second person find out the same value. Okay, Mr. Rauscher. Okay, thank you very much. So, if we doping level of 10 to the power of 16 corresponds to a distance of just 0.367 electron volts to the intrinsic value. So it is very close to the center, you know? Okay. Uh, that's it. That was my intention, so that you get some um, feeling where we are with the Fermi level based on calculations compared to the um, doping concentration, which is normal, 10 to the power of 16. Okay, so Check. That's all. Now we talk about a topic after the coffee, which is the degenerate semiconductor. Degenerate semiconductor, right? What does that mean? You can, you should, you have to uh, provide an access to the semiconductor to the physical world outside the semiconductor. So you have to have an access to the semiconductor. But if you have a semiconductor which is doped and say, okay, I place a metal on top of it, and then you expect that the semiconductor is conductive through the metal to the semiconductor, it's not really true. It is conductive into the one direction, and the other direction, it blocks the current. This behavior, one second, sorry, this behavior is called diet behavior. It is a Schottky diet. So if you just place a metal on a doped semiconductor, you get a Schottky diet. But you want to connect, for instance, the leg of a device to the semiconductor so that you can put the current through the semiconductor. Therefore, you need a so-called ohmic contact. Ohmic means, like an ohmic resistor, the current should be able to flow in both directions, through the metal to the semiconductor and back. And this type of contact is generated if you dope the semiconductor so high that the doping level itself gets a band edge. What we have said at the beginning of our lecture about the band. If we have many atoms side by side, the energy split and we get a band. The same holds true if we dope heavily. So the dopants themselves get a band edge. So the dopant manipulates the band gap, it lowers the band gap, um, and therefore you have a situation which you have also in metals. You have the situation that the Fermi level is above the conduction band edge. What does that mean? The semiconductor has, although you have no temperature, all the time free electrons. That's the case in the metal. You lower the temperature, you have free electrons. You go down to zero, you have free electrons. It is conductive. In the semiconductor, if the Fermi level is below the conduction band, you see the Fermi Dirac statistics. If you go to zero voltage, you have no probability of electrons in the conduction band. So the semiconductor is isolating. If you want to have a semi-metal, you have to increase the doping level so that the Fermi level is above the conduction band, the new conduction band. And this degenerate semiconductor is called, is used for ohmic contacts. Okay, so high doping concentrations, the localized impurity overlap and do themselves generate a band. Okay, so we reduce the band gap. We have talked about that topic. The Fermi level is above, below the corresponding band edges. The degenerate semiconductors are used for ohmic metal semiconductor contacts. So if you these type of contacts are used some slides later, for instance here, we will learn on page 44 that on an N-type semiconductor, P-type semiconductor, we place metals, and we expect that the current flows in both directions. That's the purpose. Okay, so go back to our actual slide. So that's all about the degenerate semiconductor. We generate ohmic contacts. The learning objectives, I have tried to summarize them by placing some questions which you should be able to either answer using the slides I have provided or by just listening and following the YouTube videos in the links in the corresponding slides. So the basic semiconductor physics is now continued to the motion. So where we are, we have we have a story. The story is semiconductor. So we have the crystal. Then we have the movable carriers, the free carriers. Why we need them? Because we want to move them. Why? Because we need the current. Why? Because that's the purpose of the device. Current, control of the current. Now we have the carriers. Now we have to learn how and why these carriers move. What are the mechanisms the carriers push to the movement? After we have learned the movement, we can calculate the current. So these steps we have to go through. Now we are on the step movement. Let's talk about the drift diffusion movement. The drift. The drift movement is caused by a force. So, what is a force? You can you can just force by electric field if the carriers are charged. If they are not charged, you can force it by physical push. Also, magnetic force can be a cause for a movement. So this type of current is called drift. The diffusion, you know it all. If some students don't do stuff in the lecture room, they should, if they do stuff they should not do. Give some gases. So if somebody gives out gases, you smell it sometimes later somewhere else. So this movement is diffusion. So the molecules, the particles, are not pushed. They are here. You have here a higher concentration compared to there. And this concentration difference does push the particles. So the engine behind the diffusion current is the difference in the concentration of the particles, not their charge and not a force outside the system. Okay. And if you put these together, you talk about convection. Both together is the convection. So these are the vocabularies we are talking to each other. So for what we do the motion? We do the motion for the current. as we are not interested in the absolute current level, but as we are interested in the current per area. Because if you want a high level of current, you make a high area device. Basically, that's the case. Hey, Mr. Luca, you have your arms are disappearing. Cut it up. No. The current density is the point, which is very interesting. If you increase the current density, you can smaller the device for the same current level. Therefore, let's talk just about the current density. And what is the current density? That's the number of particles per volume which are charged, and these particles are moving. So close your eyes and imagine the room you are sitting in are full of particles, dust particles. You don't see it, but they are there. Imagine these particles are charged. Now imagine these charged particles are moving effectively in one direction. This is the current density. That's all. So particles in an area which are charged are moving. This is the current density. We are now about to calculate these values. How many charged particles in a volume are present and how fast they are moving. Okay, so we have to therefore to give more names. So the current density is J. The number of particles which are charged in the volume is, yeah, the number of particles. This is the carrier concentration times the charge. That's it. This one we have already. This one we know already. Therefore, we know the charge, space, charge, concentration. Space, charge, concentration. The concentration of charges in the space. Okay. V is the carrier speed. Yeah, that's sure. And Q is the elementary charge. Okay. So now we know the current density, basically. Now let's take a look at the origin of the movements. So again, we are talking about movement. So thermal movement. For the thermal movement, the electric field is zero. The magnetic field density is zero, Tesla. But the temperature is above zero. That's the important point. This one. What does it mean? For all particles, you have this condition. The energy, the thermal energy of movement in one-dimensional systems is a half of kb times t. So if you have only 1 degree of freedom, you have this energy. If in the physical space of 3 dimensions, so in the physical space of 3 dimensions, you have 3 times this energy. That's all. That means the thermal energy, the thermal energy we have, and but we want to know the movement of these particles. This is given by natural laws, and this is the equivalence of this energy because we know we have a movement of the particles at a certain temperature. Therefore, the thermal movement of the particles, the V, is 3 times the Boltzmann constant times the temperature divided by the effective mass of the particle. The effective mass, not the real mass, because we are not talking about the electrons in vacuum. We're talking about the electrons in the semiconductor. Therefore, the effective mass. Remember, the effective mass is a function of the EK diagram and the banding there. Don't forget this correlation, the banding. So 1 over the banding, you know. Now you say, okay, I heat up the semiconductor and the current flows, and the speed is 10 to the power of 7. No, that's not the case. The speed is effectively zero because the movement is random and in the mean movement is zero. But you see, it is a very fast movement. So the thermal movement has a quite high energy, but effectively you don't leave your position due to this is the statistics. Okay, thermal motion is done. Now we switch on the fan. So you push the carriers now by an electric field or pull, whatever you prefer. So the electrons move anti-parallel and the holes move parallel to the electric field lines. What does that mean? How is the electric field line defined? From the positive charge to the negative charge. The electric field line, the vector is pointing at, from positive to negative. So we place it here, positive, negative, and the electric field lines are this way. Okay? Where is the electron moving? The red one. In which direction? For sure, in this direction. So it's anti-parallel. And for the holes, parallel. So this is the sentence at the left side. Charge carriers are scattered in electric field of the impurity ions and at the lattice atoms. So let's talk about this sentence. Only this sentence. What does mean scattering? Scattering means you disturb the linear movement somehow. That's scattering. So I take now an electron and this is accelerating. If this electron accelerates and if this movement is pushed into another direction, this electron is scattered. There are basically two mechanisms who does promote this scattering. First, the single atoms in the crystal. So if the electron is scattered by the atoms in the crystal, then you talk about scattering at the lattice atoms. That's called phonon scattering. Now you have not only the atoms, the neutral atoms in the lattice, but you have also the dopants in the lattice. What has done a dopant? A dopant of phosphor has donated one electron. This electron is moving. We are talking about this moving electron. But the phosphor atom is no more an atom, it is an ion. It is a localized, because it is bound to the lattice, it is a localized ion. It is one times positively charged. So if we have now here the phosphor and here the electron is bent in its trajectory around this charge, you know? And if it is a boron, then it is uh, abgestoßen. Distracted? No. Repelled? Repelled? Bota, I would like to listen to you, but your microphone is off. Yeah, I love your comments. Thank you for the English lectures. So they repel if both are negatively charged. Okay, so this is the impurity ions scattering. So we have talked about this sentence only, not more. Let's go on. Through these interactions, they partially release their kinetic energy. So I have an electron, I have an electric field, I have an electron, and this electron is on the move. And if they are scattered, they partially release their kinetic energy. That means they transfer their kinetic energy to the lattice by phonon scattering at the lattice atoms or by at the impurities. Both means that the energy from the movement is transferred to the lattice. What is energy in the lattice? Temperature. You rise the temperature. Energy in the lattice. You rise the temperature. That means if you have moving particles in the lattice, you increase the temperature due to the movement. And that's the cause of the ohmic resistors. If you have an ohmic resistor, it is not a vacuum. There are some electrons inside this material. What is voltage? Voltage is voltage in a distance, is electric field. I repeat, electrical engineering, first semester. You apply 1 volt in 1 meter, you have 1 volt per meter electric field. And this electric field does generate a movement. This movement is not increasing, the speed is not increasing into infinity. It is increasing, scattering, increasing, scattering, increasing, scattering, and this results into an effective speed. So you have a speed overshoot, so the speed increases and then decreases due to the scattering. Then it increases again. And in the mean value is the drift drift speed. I have it somewhere here. Drift, it is within the drift current density. Oh, here. It's missing. It's missing. I have deleted too much. It's the mean value of the drift speed, drift velocity. So the drift velocity. I just put this text here in. That's the drift velocity. Okay, here we are. Something called the drift speed. Okay, drift velocity. So some parts are left um, from the professional translators. So they have said speed, and I have assimilated this word. Excuse me. In semiconductors, we say velocity, not speed. Okay, so what is the drift velocity? It is proportional to the electric field. Sure. And it is proportional of this time constant. What is this time constant? It is the average time between collisions. Hmm. If I have an infinite distance, if I have any electric field and no collision, again, I have infinite distance, a certain electric field, no collision. The speed goes up into infinity because for each distance you gain energy. But in the matter, in the silicon, you are scattered. And if you have in average this time, you have in average this electric field and this time to generate velocity. Can you follow up these logic steps? So this is the force you pull. This is the time when the speed goes back to zero because of the scattering. You have a mathematical expression for this value. So now, what is physically defined? Physically defined, we have, one moment, physically defined, we have the elementary charge, we have the effective mass, it's physically defined. Due to the fact that it is a matter, it is a crystal, we have also the mean time between collisions. We have this area. This is physically defined. The only value you can manipulate is the voltage you apply. This is the electric field. Okay, this means this is the mobility. The drift velocity is a function of the mobility times the electric field. And the mobility is the rest I have had at the top. So what is the mobility? Is the ability to move. If you have a lot of mass, then your mobility is reduced. If you have a lot of collision, you have a long time between collisions. You have a large value. You have a high velocity, high mobility. That means increasing the mean time between collisions increases the mobility. Increasing the effective mass, reduces the mobility, for sure. But this is a simple equation. This equation I just help you to transfer its meaning to your brain. So this holds true also for the holes. This perfect question. I have had during my study time also the question, but nobody has answered me. And they said no time, no time. So I have taken the time to find that out. If some students like you drop me such questions. And this is the one moment. I haven't put it here. Oh, lifetime. It's not the same. Hmm. I have the results here. You see this? So the mobility is a function of the temperature. This means somehow this variable, this constant, changes with temperature. And and we have also some more, yeah, some more stuff we have to take into account. Now we have to go back to one certain slide. What is the mass of the electron? This one. And the mass does change with the energy. This means the electrons does not behave like a particle in vacuum. The electrons in the semiconductor does behave differently, and this difference is expressed in this curve shape of the EK diagram. But basically, the electrons are here, therefore they have a certain effective mass, and therefore, in a certain limited assumptions, the mobility is constant. Because my mobility is constant. I have a mass, I have a certain time between collisions after drinking, so I have a certain drift velocity. And this holds true also for the electrons. But we will talk about the change of the mobility also, but not now. At the moment, we say mobility is constant. We keep it simple. Okay, mm, we are here. So the mobility is constant. We increase the electric field, we increase the voltage we apply, we increase the speed. That's it. Mhm. Um, no, the tau c is constant for a certain temperature and so certain doping levels, certain material. So this is constant. So if you increase the voltage, so the electric field is V divided by the distance. So if you increase the voltage, you increase the speed, and the mobility is constant. So you assume that tau c and me is constant at the moment. Okay? So the average time between collisions is constant, and the effective mass is constant. So we have only one proportionality. It is the drift velocity is directly proportional to the applied electric field. That's it. Okay? Good. So now we can calculate what we have talked about. We have charges in the space, certain number, which can move. At the moment, we have talked about this movement. Okay, let's take this equation and calculate the current density of the electrons caused by drift. This equation I have just copied. This speed I will insert. This space charge density I have copied. So here we have, one moment, here we have the space charge, and here we have the velocity. So we have this equation. That's it. So what we see for the current concentration, current density. The current density is proportional to your doping. Who does produce this N? This N is roughly ND. You are causing this number of carriers per cubic centimeter by doping. Also, for the holes, you are causing roughly by acceptor atom doping this number of carriers per cubic centimeter. Okay, so keep it at the electron side. The mobility is constant. So we have it. And here you have the voltage. So this is the ohmic law. You increase the voltage, you increase the current. We have derived the ohmic law at this situation, but we have two components, the electrons and the holes. Because if you have a semiconductor, you have electrons moving antiparallel and the holes moving parallel to the electric field, to the voltage you are applying. So both components are acting additively. And therefore, you see, this negative value is, 1 second, compensated with this minus. Here we don't have a minus, but we have also a not minus charge. So both currents are a scalar value in the same direction. So you add it to a sum of current. So this current density has two portions. Now I have a question to you. If you have understand doping, you can answer the following question. If you have an N-type semiconductor, which portion of this current is negligible? Now I have it, negligible. Which portion of this current is negligible? This or that? And give me the answer why. Oh, that's a donator. Uh-huh. Yes. So if you donate, you have a lot of electrons. Therefore, these are um, majorities. So this one, for this case, is dominating, and the minorities, it is negligible. Exactly. This is the logics behind. That means if you have a certain Herr Müllerschild, guten Morgen. He's gotten away. Hello. And so if you have a certain type of semiconductor, sorry, this content is very, very, very dry. So take a cup of coffee. Okay, so if you have a certain type, doped type semiconductor, you can reduce the effort to calculate both components. You can skip one because the relationship of the values is millions times the difference of the other one. Okay, now I have this part extracted. What is this time? This part, it is the total conductivity. So the conductivity, and what is the 1 over the conductivity? It's the total resistivity. Resistivity. So the ohmic law. That's it. So now all you can say about this and this gives you the resistivity or conductivity. And some of you has told me if we increase the doping, we can increase the conductivity because we increase the number of electrons, for instance. And I say, if you increase the number of electrons, you increase the disturbance. Why? Each phosphorus atom is a phosphorus ion. It is charged 1 times positive because it is donated 1 electron. So if you have now an electron moving around, it is detracted. So this detraction, the scattering, reduces the mobility. And about this topic we are now talking about here. But before we go there, I have something different, which is at the first glance not possible. You have a resistor, you apply a voltage. If you increase the voltage, the current increases. Is it true? Yes. In our case, what is the current? It is a function of the number of electrons and the speed. If we increase the voltage, we increase the speed. Therefore, the electric field speed is a constant if the mobility is constant. This is the same diagram if you put this way: voltage, current, increase. And this is the resistance in ohm. This is the equivalence to this line. Constant. Oh, fuck! My pencil is empty. I have to use my fingernails. How should I? Yeah, okay. So the finger pencil now I have to activate, but it's not so easy. I have to switch off uh, the electronic pencil. I doesn't mind. I will talk 5 minutes and then I gain some half an hour of using the pencil. I'm talking now. So the constant, no, this way, no, this way, yeah, this way. The constant slope means the resistance is constant. But in reality, in the silicon, if I further increase the voltage, the current doesn't increase anymore. This is the area of constant velocity. Can you tell me, can you imagine how we reach the constant velocity area? Why the semiconductor is in a certain area, like an ohmic resistor, and if we increase further the voltage, everything is constant. Why is it the case? Uh, the probability of the collisions does not change. That means, so we are talking about this. So the probability of collision doesn't change. The elementary charge doesn't change. But how it can happen that the mobility is no more constant, but the velocity is constant? How this can happen? You increase the power, you increase the force by increasing the voltage, but you don't increase the velocity anymore. Again, again, please. So the speed, the noise cancellation uh, blocks parts of your sentence. You speak up louder. You have to speak up louder. So the increase the voltage, you don't increase the speed, but you should increase the speed because of this equation. Now the only variable or only value which can change is the mass. So in reality, my mass doesn't change. We are also not relativistic, so the speeds are very low. But now we have to go to the point where I have given you the hint that the effective mass will change. If you increase the energy, if you increase the velocity, you are here. So you cannot increase further the energy because the mass is increased. Can you imagine that? So you are no more here in the silicon, you are here in the silicon due to the increased energy. Therefore, as this is in the denominator, the banding is reduced, sorry, the banding is reduced, the mass is increased heavily. And therefore, due to this condition, you have, one second, you are no more increasing the speed. The speed saturates to the saturation velocity. And if you have this curve in your mind, you have also voltage, current. For a transistor, you have these type of output characteristics. This is the reason why it is the case for JFET transistors. JFETs are doped materials, and the current increases to a certain value, and then no, this way. uh, I'm a little bit yeah, you have the slides in front of you. I see me in the slide, and I'm a little bit disoriented. Yeah. Um, So therefore, we have constant mobility and constant velocity areas within the characteristics. Okay, so the constant velocity, we have it. So we have some values which are element, doping, and configuration dependent. Let's talk about that. We have the mobility. We have seen that the mobility is no more constant if we increase the speed. Before, so before we reach this saturation, we have also some functions of doping and something else. Let's talk about the temperature. We have, after this slide, we are for today over. So keep you motivated to catch the content. If we increase the temperature and if we have a doped, so donator, acceptor, I don't mind. If we have a doped semiconductor, if we increase the temperature, the mobility increases and then it decreases again. How you can imagine this could happen? So effectively, you heat up and the mobility increases. And you heat up further, the mobility decreases. The reason is for low temperatures, the impurity does play the dominant role. For high temperatures, the lattice itself plays the dominant role. How? How does that happen? If we have these impurities in space. So what is this type of semiconductor? Is it N or is it P? Hmm? N-type, because it is a donator, so it has at least 1, 2, 3 electrons released. Okay, let's talk about one electron. The trajectory of this electron is somehow this way, and this way through the semiconductor because of the impurities, attraction, the Coulomb scattering, because of the Coulomb law. Okay? If you increase the temperature, the movement of the electron does also increase. And the Coulomb scattering, the force, it tries to catch up the electron, is getting less. So we are talking qualitatively. If the electron is moving more, or if this impurity is moving more, then its effect is verwischt. Verwischt means it is verwischt. Verwischt. One moment. Its effect is, huh? Diminished. Yeah, great. The effect is diminished due to its time of effectiveness is distributed on more greater local area around its center. Therefore, the scattering reduces due to the Coulomb attraction. And then some different effect, which is ideally has this type of effect, the intrinsic atoms. So if you have a constant not moving atom in the lattice, the electron passes. If the atom is moving heavily due to the temperature, the probability of collision increases. So this probability increases and the mobility decreases due to the intrinsic atoms. So this tendency of having less impurity effect and the tendency of having more intrinsic atom effect overlaps, and the dominant areas are characterized this way. Let's go to here. Do you see the measurement 1, measurement 2, 3, and 4? What has been measured? All these dots are measured. As a function of the temperature, the mobility is measured. What is a variable between black, red, green, and blue? They are the doping concentrations. So the black one, 1, has almost no doping. It is, like I have said here, the mobility just decreases as a function of the temperature. And if you increase the doping level, you increase the number of impurities, so you reduce the mobility. And by the reduction, you introduce this slope. Let's go to the measurements back. So number 4, we have a doping level of 10 to the power of 17. So here it is. Okay, so here we have the 10 to the power of 17 per cubic centimeter. Okay, so this means we have the increase due to the impurity release and the decrease due to the lattice scattering. So these two areas is reduced to, in my lecture notes, to, one moment. In my lecture notes, it is just this sketch and this sketch. If you have the book Mauro Zambuto, you have these curves also there. From Mauro Zambuto, I have this picture. So low doping, I have only lattice scattering. High doping, I have the increase in the mobility due to the reduced effect of the impurities and the expected lattice scattering effect, which is dominating here. Now let's talk about current density. I want to compare the effect, so it is proportional. The electron drift current is proportional to the density of electrons, you know. So the electron drift current is proportional to the number of electrons and to the mobility. Let's assume your voltage is constant. You're applying. So here we are. So the voltage is constant. So we have proportional to the electrons and proportional to the mobility. What happens if you apply, let's say, 5 volt? What does change with the current? Does it increase or is it reduced? Let's take a look. Let's assume we are here. Okay? We have, at this temperature, this mobility, 100. At this doping level, And if we have a almost intrinsic one, let's take this value. So I'm simplifying the value. So, so at this value, we are here. Here means, one moment, 50, 60, 70, 80. Uh, it is not very, 1, 2, 3, 4, 5, 6, 7, 8, 9. It is just 9, not 10. There is missing one line. Doesn't mind. So it is here 1,900. Let's say this is um, 800. Let's say, roughly. Okay? And here we have 100. So the mobility is reduced by a factor of 1 over 8. It is 1/8 of the original mobility. Hmm. How much is the doping concentration changed? So this is your N. Don't forget that. This is your N. And here, this is your N. This is your N. And now let's go to green. This is your mobility. So if we increase N by times, let's see, 19 to 14 to 19 by 10,000, no, 100,000 exactly, we reduce the mobility by 8. Okay, you were right. If you want to increase the current density, you have to increase the doping concentration. Although the mobility is reduced, that means your increase in doping is not one by one. So the increase in doping concentration is not increasing the current density one by one. It is reduced by a factor caused by the mobility. Again, this sentence. If you increase the doping, you increase the current, but not with the same factor because you reduce the mobility by increasing the doping. I would like to you to know this forever. How you get that? I don't know. I just can help you by putting these links to you, the lecture notes from the recording. I hope it has worked. And yeah, by keeping not asleep, Mr. Miller should, you know? I got you. Okay, so for today, it's all. I would say I stop here. Today, it's the 5th of May. Hey, 5th of May. And from the content, it's over. Do you have some questions? No? Then have a good evening. Bye bye. See you next week. Ciao.